Good morning, everyone. So welcome to this VOD I will provide. So today is like the last chapter. It's called Evaluation. So we're to to place this in our whole lecture schedule and our lecture structure. So we started out with business understanding, went to data understanding, went to data preparation. Then we spoke about modeling. So this was the most recent step where we talked about how we could apply machine learning to linear regression, logistic regression. And in the next lecture, we will also talk about ANN. So this will not be part of our lecture, but I moved it towards AIVDS2. So don't wonder. I just wanted to include this because it actually will be about modeling. So in the next semester, we will exclusively speak about modeling and of course evaluation. So this always goes hand in hand. So today we're going to talk about three topics. The first topic actually belongs to data preparation. So it's kind of at the end of data preparation. We will talk a little bit about how we're going to do this. So we're going to talk about data splitting because a really essential thing in machine learning is that we want to test our model on a data set that has been untainted and a data set that has not been used for training. This is very, very crucial. So you can imagine like you're going to prepare for an exam, like I give you the mock exam and you have some exercises, you have the slides and you prepare for the exam, but you don't actually have the exam to prepare for the exam. If I gave you the real exam, you would all perform very, very well because you know the questions beforehand. So in general, this will not help us in creating a model that could predict future things. For example, we had two examples. The first example was a regression example in modeling where we talked about using the hypothesis form of linear regression and we predicted housing prices in Portland, Oregon. So now imagine I want to predict the price of a house and I actually have this exact house in the training data set. So the model would actually know the price of the house. So this can basically not happen. So the second was the example of detecting cancer, if the cancer is malignant or benign. And so if we actually had these cases with the exact tumor size and the decision, the model would tend to just use this solution. So we try to avoid for the model to have all the data. So what we do is at the end of data preparation, um, nearly at the end. So there are some steps in data preparation we will only apply to the training data set and not to the test data set. And I will talk a little bit about that in a few seconds. However, at the end of data preparation, we're gonna split the data set usually. There are many techniques to do this. So this will be our first topic. How can we generate a so-called test data set that is apart from the training data set, right? So basically, just as I said, so we have at the beginning of it all, we have all data, right? So we have all our data, we have a table, and then what we're gonna do, we're gonna split it into a training data set. That is the only data set we're gonna use to train our model, right? And then we have a so-called validation data set. We can also have a test data set. I'll talk a little bit about this. Sometimes there's a third data set here, but usually it's just these two. And we're going to train the model on the training data set, and then we're going to test the data or validate the model on the validation data set, right? To see how well the model performs. And then we're going to deem, is it useful or not? And if it's not useful, well, we know that this CRISP-DM process is an iterative process. So we might want to go back to like data understanding, data preparation, or modeling. Like we can do any of these iterative steps back to improve our model. So this is the step where we actually check how well our model performs on an unknown data set. So there are some things and some ideas here. The first idea why we don't use the training data set is that the model needs to generalize, right? So it needs to generalize to data that the model has not seen before because we will use it for the future. So we are not interested in describing things that have already been taken place. So it makes no sense to use purely the training data set, right? So the question now is, how can we split these up, right? So how can we split these up? So first of all, let me tell you that before we split that up, so this is usually done at the end of, we can do this at the end of data preparation since this is a data preparation operation, so to say. The first and most important thing is that we want the validation data to be untainted, right? We want the real data in there. So whenever we have a step in data preparation that generates synthetic data. And by synthetic data, I mean we add rows to the data. We shall not add them to the validation data set. So as an example, what we do not want is, for example, if we use a method that generates data. For example, if we are oversampling a minority class. You remember when we have class imbalance, right? We had, for example, we could do SMODE that also oversamples, so it generates synthetic examples, and we do not want them in the validation data set because they're synthetic. They don't reflect the truth. They don't reflect ground truth. They are just there to train a better model, but we will always test on untainted data, right? That doesn't mean that we can't do any other preparation here. For example, if we generate variables out of the variables we have, for example, we have a date column and we want the date of the last purchase, and we generate days since last purchase. This is allowed since this is just derived, and we could derive it in the real world too. Now, if a new customer or if a customer comes in where we want to predict when the next purchase is going to be or how much the next purchase is going to be, we will have the date of the last purchase usually, right? So we can still transform this with a new customer. Also, when we sell a house, right, and we want to derive some things in the house, like we want to derive a score or something, or we have the address of the house and we want to derive, for example, a score on how good the location is. We can do this because we have the location, right? So all these things are okay in the validation data set because, well, with the validation data set, we need the same columns, the same variables as in the training data set. So everything that generates more variables is okay. We can use it and we need to use it. Otherwise, we cannot apply the model. Now, for example, if the model needs days since last purchase, as for example, the variable x4, right? Then we need to put it in to validate the model, right? So we need to generate these. However, whenever we generate rows, new cases of data, we don't want that in, right? Because it's synthetically generated data. So this is very important. This is the large difference. So columns, yes, basically. Rows, no. Okay, this is the rule. So we only have these synthetic rows in the training dataset, but not in the validation dataset, because we want the validation dataset to reflect the real world, the real cases. Okay, so now how can we split this? Well, there's basically the first thing where we just say, okay, we're gonna do what's called simple random sampling, right? So simple random sampling is pretty easy. We're just gonna put all our data, right? We're gonna put all our data into a head, into a sorting head. So these are the axes are cards from all our data, right? And we're gonna have a ratio. For example, we have training 70% and validation 30%. So this always obviously needs to add up to 100. And then we're gonna draw 70%. So if we have 100, if we have 100, then we're gonna draw 70 here and we're gonna draw 30 here, right? 30 rows here. And then we're only gonna train the model on these 70 rows. This is basically it. And we do this randomly, right? This is purely random. So this is why we draw it from a hat. There can be no systematic, like take the first 70 because we don't know how they are sorted. So basically this is it. Okay. The next one is the more sophisticated one is k-fold cross-validation, right? In k-fold cross-validation, what we actually do is we take all the data, right? We take all the data, but what we do is so this is all the data, right? We're gonna partition it into k, so this is why there is a k here, into k partitions. Usually k is 10, like tenfold cross-validation, tenfold is kind of the standard. Like sometimes we use more, sometimes we use less. It depends a little bit. So in hardcore deep learning models, tenfold cross validation can be a little bit hard on our hardware. So we use maybe fivefold, but usually we will use tenfold. Okay. So we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 partitions in a 10-fold cross-validation. So, and now it's pretty easy what we do. Now here in the what I've drawn in red, so the simple random sampling in red, what we're gonna do is we're gonna train one model based on the 70%, and then we're gonna test it on the validation data set, and we get some metrics which we will speak about in the second part of this lecture, right? Now here, what we're doing is we're gonna train K models, right? This is very important. So here we train one model, and here we train K models. This is very important, and people miss that, right? Train K models. We train K models here because what we're gonna do is for the first model, in the first model, this will be the validation data set, right? And this here, this data set, so all the other partitions will be the training data set. Train, right? And in the second model, we will have two be the validation data set. So this will be the validation data set, and training will be data set 1, and data set 3 to 10, right? Not 2, of course, because 2 is the validation data. So this is 2, and here the validation data is 1, and here the training is 2 to 10. Okay, so this is it. This is k-fold cross-validation, and we get 10 models. So this is very crucial. We don't get one model, we get 10 models. And what we do is we then measure for each of these, we measure the performance based on the validation data set. So we have 10 performance metrics. So for example, we have, if we measure accuracy, we have here like 78%, right? Here we have 74%. And then we go on, right? And then what we're gonna do is we're gonna average this, right? So and then we have an average after 10. After 10, we have an average, and the average is like spit out, right? So let's say we have this as an average accuracy. Now, what are the advantages of this? And what are the disadvantages of this compared to simple random sampling? So in simple random sampling, we only have like one. We only have one metric based on these 70, based on this 30%. We train it on the 70 and on the 30. Here we build 10 models, right? So what's the difference? Okay, so in k-fold cross-validation, what are the advantages? The first advantage is obvious. Now we basically have a larger amount of training data, right? Because each model is trained on a larger portion of the data usually than when we have this fixed ratio, unless we have a really small validation ratio, right? Which we usually should not have because some of the data should be captured. If we do have here, for example, a small ratio, so with small ratio, I mean this percentage gets way down, let's say 5%. The problem is that we don't catch all probable cases in the validation data, so we cannot properly test if the model reacts to all kinds of cases. So the larger this number is, the more we can react. On the other hand, the larger this number is, the smaller this number gets. So the model gets less and less trained on these cases. So we have to find a middle ground here, right? So in cross-validation, this disadvantage kind of vanishes because each portion of the data is one's training data. So we basically have one model. So for example, this first model here, it actually only does not see the first part of the data and the rest of the data, right? So, and of course, in k-fold cross-validation, what we're gonna do is we're gonna have 10 heads, and we're gonna sort all data also randomly. So this is like also not a systematic, like they will be randomly assigned. We just have like 10 heads, just 10 bins, sorry, and we have one head, and we randomly draw and put them into the heads until they have the same amount of data. Now, if we have 100, if we use the same thing, if we have 100 data rows, that means that each of these k-fold of these k bins will have 10 rows, right? And we randomly assign these 10 rows. It's also randomly assigned. So this is basically k-fold cross-validation also works with simple random sampling, but sort of we have the notion that we put only 10 here, 10 here, 10 here, 10 here, 10 here, and so on, right? But this will also be random distributed, right? The simple random sampling will be distributed from all data through simple random sampling to these bins. So the advantage is we will use less training data, okay? The other advantage is that we get a better idea of how stable this is and how the models react to these performances. We can also put out a standard deviation of this performance metric, right? So we see how strong it varies. So it could be that some models actually are pretty bad and others are pretty good if they like catch sort of a weird, either a weird test or weird training data, right? So we can have some sort of, we can answer the question of stability of the model, right? So we could, for example, also draw a box plot over the 10 folds. So basically we have a box plot here. This is the accuracy, right? So we have this right here, and we only have this one box plot. And so we have here this in this box plot, we have all these different our 10 folds, right? So basically these are our 10 folds. So this is fold 1. They're pretty close together. A lot will be in here. There could be like an outlier, like somewhere here. So we have one good model and maybe a bad model. Now, if we have something like this, this could potentially mean that we are under maybe some sort of performance threshold that we got from business understanding, where we say it shouldn't be below that one. So, and then, so if this is the median here, right, in a box plot, this is the median, we might prefer a model that has a lower median performance, but that doesn't go below that threshold. This is very important, and cross-validation kind of enables us to see this. Okay, now what's the disadvantage of cross-validation? Well, the first disadvantage is that it takes way longer because instead of training one model, we have to train 10 models. And we train the models based on a lot of data. So we train the model based on 90% of the data all the time. So we have a 90% training data all the time. So we train 10 models with 90% of the data. So it takes longer to train for each model compared to one time using simple random sampling. And we have to do this 10 times, right? So it's computationally more expensive. Now, if we have models that take a long time, that are very computationally expensive to train by themselves, like some deep neural networks, this will take a way longer time. So the training time increases manifold, okay? And the second thing, it's not really a disadvantage, so to say, but this is something we have to discuss. And this would probably be your first question right now is, Kai, hello, we train 10 models, but what model do we deploy? Because we know after this, we have another step that is called deployment, right? So we need to deploy a model. Now, which of these 10 models do we deploy? And the answer is what you usually do in practice, right? Is you make sure that there are none of these really bad outlier thingies. And what you do, then you'd select, because usually you train some other models with other hyperparameters. Maybe you do train a deep neural network, you train a linear regression, you train an SVM, and then you compare them based on these numbers. So you do tenfold cross-validation on many hypothesis forms, like to get the best model. That you can, like you test many hypothesis forms, because the hypothesis form is something you decide, remember? So basically you have a benchmark then. Let's see, you have a benchmark here. So for example, you have an ANN, you have a linear regression, and you have a support vector machine, you have an XGBoost. So these are all forms of hypothesis, right? So these are hypothesis forms. And so here you have, for example, the accuracy performance, right? Let this be a log regression. So because we learned that we have a classification. So this is logistic regression now, not a linear regression, sorry. And so what we're gonna do, and then we have like this average accuracy. This is the average accuracy of tenfold cross-validation, right? Tenfold XVal. Okay, so we have this accuracy here. Maybe we have here also the standard deviation of this. So we have the accuracy, like this is 91%. Usually it's 0.991, but I'm going to do it in percent. This is 87, this is 92, and this is like, let's say 93, because XGBoost always wins. It doesn't, but it's really strong model, okay? And then we have the standard deviation. I'm not going to put them in here, but standard deviation will be important. And then you could also can do, then you have like these box plots, like for all the models. For example, you can have this for ANN, right? For log regression, for SVM, and then you can compare them, right? And you can suddenly compare these models using the tenfold, like the same way we do this, but and then sometimes if we see something like this, so the ANN might be a very good model, but it has like sometimes it really goes astray down below a certain performance threshold, which we cannot use. So this model will be out now. Like, so we use this to select models that adhere to our kind of model. So we, for example, want to say we cannot use this because of this, right? So, and this is the whole idea. And now back to the original question, which kind of points, so which kind of these points do we use? Because we have 10 models, right? We have 10 models. We have 10 models for ANN, 10 models for this, 10 models. So we look at the average and then we decide which class of model we want to go with. So let's say we decide for XGBoost, right? We say, okay, XGBoost is nice. Okay. And then, of course, we have 10 XGBoost models because we did 10-fold cross-validation. So we have 10 of these models because this is just an average out of these 10 models, obviously. So let's say we say, okay, we're going to go with XGBoost. What we're going to do in practice is you then going to retrain your model. You're going to use the same hypothesis form with the same hyperparameters that you used to train this, but you're going to train on all data. Because you want the model to be best prepared. Because now we know the performance of the model on unknown data, and now we can train it on all data, so it doesn't accidentally has left out mechanics that are maybe in this in some of these models. Now, if we use this model, for example, we don't have the data sets that are in 1. If we use the second model, we don't have the data sets that are in 2, right? The data rows that are in 2. And once we have evaluated this, it's very important to evaluate it first so that you know how the model would react to new data. But then you basically can use all the data in practice. Why would you throw that away? So basically, the deployment model would then be trained on all the data. That's it. Like, this is the practice advice. Okay, so now that we've spoken about this, what are some general things that can go wrong? And this is the one you've all been waiting for. So what do we do now with these numbers, right, that we have? And there is a big thing coming that when we fit a model, so fitting a model is training a model. And for example, here we had different hypothesis types, right? And if we fit different hypothesis types, we tend to just evaluate them. We want to evaluate them, right? So, and there are basically two things that can happen when we train a machine learning model and we evaluate it. So the first thing that can happen, the model can overfit the training data set. And what do we mean by overfitting? It's pretty simple, right? Imagine same situation. You prepare for an exam, right? You prepare for a math exam. And when you prepare for a math exam, you try to calculate as many tasks as possible, right? And now let's say the problem is you just learning a lot and you, instead of learning how to do the actual task, you learn the tasks by heart, right? So you learn it by heart and you are very good. If the same task comes on, you are very good in doing this. But if a new task type comes on, you have no idea because you basically learned the training data set by heart. So this is overfitting. So it overfits to the training data set, right? And we can see this here. If we have this chart of the prediction metric, right? So we have this chart of the prediction metric. And the prediction metric is like let's say it's the accuracy, right? Let's say the prediction metric is the accuracy. So better accuracy, higher accuracy is better, right? So the higher it goes, the better it is. And Now here we have model complexity. So model complexity means so we train different models. For example, we can train an easy model that has like only one variable, right? So we have like one variable. This is easy. So a linear regression could be somewhere around here, right? This could be the LR model. So LR, right? And then we could have a very weird ANN that looks like this with very many hidden layers and stuff like this. So this is very complex. Don't worry, we will learn how to build these in AI-BDS2. So very complex model. So this is this has low complexity, low complexity. This has high complexity, right? So usually this also means that they are prone to overfitting. If they have high complexity, they usually are prone to overfitting. So and here will be maybe somewhere will be this ANN, right? So um, and the problem is what you will see, and you can explore this, right, in a graph. If you have, like, you can also have the linear regression model, and you can gradually, so for example, you can gradually, let's call this LR1, you can gradually add more stuff to it. Like, you can do this, x1 plus x1 squared plus x2 plus x1 times x2 and so on. So you can do the same thing that we remember the logistic regression with the where we did this. You can also do this linear regression, right? It's the same thing, just a logistic regression. We put a G around this, but it's basically the same idea. So you can add a lot more complexity to this model so that it goes maybe towards here, LR2, right? This is LR2 that. So, so you can move the complexity of one model type. You don't have to change the hypothesis type to get a more complex model, but you can though, right? So it's like this is just an abstract thing. But if you have if you have like the same model, you can usually look at this. What you also can do is like for an ANN, you know that we have many iterations that takes to train the model. So it could also be like this is, for example, the hypothesis type, right? The hypothesis type, but it could also be the iteration. Like you start with the first iteration, and the more you iterate through the training data set, right? Because you iterate with one gradient descent, you iterate through the whole training. We will talk about in detail gradient descent and iterations in AI-BDS2, but you iterate through the whole training set, and then you iterate again, and then you iterate again. So each iteration goes through one training data set, iteration 2, 3, and the more it goes through the training data set, the more it adjusts the parameters, these ones, to the training data set, right? So the more iterations you have, the more fine-tuned it gets towards the training data set. And this is why we get this picture. So the training accuracy goes up. It goes up, right? And the validation goes also up to a certain point, right? So they are in parallel basically. So it usually is not that good, but and at some point, uh, when it starts to learn the training data set by heart, so it adjusts more to training data set, it is less generalizable and less flexible to react to new data. And you can see this figure, right? So you can see they diverge now suddenly. You see this here? And this is what you oftentimes can observe when you have the iteration, right? So, and this kind of is the problem. And so out of this general thing, we have two things. Like we have overfitting. This is what we talked about. So we can see overfitting right here. So this is when this diverges. So when it learns the training data set by heart, and then we have underfitting, which is the opposite. So underfitting means that my basic model is the complexity is too low, right? So it happens like here. So the model doesn't catch the pattern because we know that in reality out there is a pattern, right? So we don't know it. This is why we try to model all the influences. We know there is some way that the Y value is created. For example, we know that somehow these houses sold for that price, but we don't really know what on earth influenced this, right? We can guess like where the house stand, how large the house is, and so on. So we can guess some of these things, and we will try to input them as inputs into our model, obviously. Um, So we try to catch that. Now, remember the housing price thing. We discussed it in the last lecture, the lecture before that, where we talked about if this is a good model. So as an example for linear regression, I showed you this model that predicts housing prices in Portland, Oregon, and we just had the square feet of the house as sorry. So we had the input price of the house the price of the house as a y variable, and the input was the square feet. So what did we do? We discussed this, and you said this is not a good model. It's too simple. We need other parameters. Like some of you said, we need the location. Some of you said we need number of bedrooms. Actually, I said that probably, but yeah. And so we need to add more variables. Like here, we need to make it more complex, right? So this is what we did, exactly what we did here. We need to make it more complex. So we need to move from LR1 to LR2, right? Um, so in order to catch the mechanisms that determine the price, right? So, and if we have underfitting here, if we look at underfitting, what happens is, so we have this pattern, for example, and our model is too simple. So you might remember the Enskombe quartet, right? Where we had these four cases here, right? And we talked about them in data preparation, and Enskombe. If you remember that, and if you remember that case right here, first row to the right, this was like a square, right? We had actually the square function, but we fitted a regression line onto it, right? So, and then all of you said, hey, this is not correct. The model is not correct, right? And this is a good example of underfitting, right? So this will underfit, definitely. So the opposite is that we have a very complex model that tries to catch every point. So here, if you look at this, we have a polynomial model that catches every point. So this is, and what do we call it? Like these two things are usually called, they have nothing to do actually with their counterparts in statistics, but they are called bias and variance. So if we have a model that underfits, like the model is biased, is highly biased, so it doesn't really catch the mechanic. So it's really biased, that case. So it has, we call it, this has a high bias, right? This model. Now, if we overfit, it has a high variance. Now, variance means that, for example, and you can explain it that way, if I add a point here, right? If I add a point to the training data, right? And the model would change. Like there's a high variance of models whenever I add a training point. Now the model would change. Now in a simpler model, like in the right model, if I add the point here, the model would barely change or not change at all, right? Whereas this function would totally change because it's a polynomial. It's polynomials to go through every point, so it would just add something like this here. And here it wouldn't change, right? It wouldn't bother. Here it wouldn't also change, right? So this is also very low variance, obviously. Like this is low variance. But this is low bias, low variance. So we fit the data, but we don't learn it by heart. Like we don't care if we add a point here or a point here. It catches the pattern, right? Now here, this is very, this adheres to the training data set, but this is less complex. So this is a high complex model, right? This is a very complex model. So let's call this model 1 and let's call this model 2, right? So model 1 is obviously right here, right? It's somewhere here. It has high complexity. It's very complex. A polynomial model that catches everything. And model M2 is like somewhere here, right? And if called this model M3, and model M3 is then somewhere here, right? It has a good balance between the two, okay? So don't get too confused by bias and variance. Like you can basically see these are just terms, right? I want you to treat them as terms and not confuse them with the bias and variance you know from statistic, right? Just take them as terms. So this is what, take it as this is what it's called, okay? Yeah, this would be great. Okay, so these are some things that can happen, and this is also very general. Like both the things I just explained, like the data splitting and the bias variance trade-off, as it's called. So if you Google bias variance trade-off, this is it. They are true for all machine learning models. So this doesn't matter if we have linear regression, ANN. So we can straight up take this and put it into the next lecture next semester. So Now we're going to evaluate, and we're going to start by evaluating classification. So we're going to split the evaluation, how we're going to calculate the things like accuracy and all these things. Now we're going to want to build metrics that tell us how good the model is. So we finally want these numbers. Like we basically want these numbers here, right? We want these numbers. We want to know how can we calculate these numbers, how are they calculated? So, and we're going to split this up for regression and for classification because it's rather different because of the different scale types of our variables. So we're going to start up because it's more complex with classification, believe it or not. And now what do we need? So I will treat this kind of like a recipe, okay? So first of all, and it's pretty straightforward. So what do we need as a recipe? So what we need is we can do this with the training and the validation. Like just because I said do it on the validation doesn't mean we can also do it on the training, but usually we will do it for the validation data set, right? But we can also do this for the training data set. So you do it for the validation and the training data set. So what you're going to do is what you need. Like this is a recipe like for a tomato soup. So what you need is you basically need two things only. So you have your validation data set. You can also do the same thing on the training data set, right? So why we do this? Because so we can compare it, right? So this is the performance on the training data set. This is the performance on the validation data set. Now the performance on the validation data set tells us how well it generalizes. So we will focus on this, but we also need to see if it overfits. So we can basically do both. And we only need two things from both data sets. So we need the ground truth. So we need the Y value. The Y value is the real value. Now in the validation data set, the model has never seen this, right? In the training data set, the model has seen this as part of the training example XY that we give, right? So, and in validation, they just know X. Now X is not part of this at all because we just compare our hypothesis, right? For the case, like this is the ID, basically, or the X values, right? So we have the X values all here. And so we just have this and we have this value. So we just need the prediction for these rows, right? So can have the X values right here, if you like, but this is the prediction. We just need the prediction value, right? And then we compare them to each other. Like we know that this is a class, right? So let's say this is a binary classification here. So Y can only be either 0 or 1. Like for example, credit worthy and not credit worthy, right? So let's say this is the truth. So this is ID 1, 2, 3, 4, 5, 6 of the validation data set. And we have 1, 1, 0, 1, 0, and so on. And then we have the prediction. And then what we basically do is we compare them. So this is the same thing as you have here. Like this is the ID, right? This is my ID. And then we have the actual classification. The actual classification we call ground truth. So this is Y. This is the Y variable, the ground truth. And the predicted classification is the output of our model, right? So this is H theta of X. So this is our prediction. This is what our model does. And this is the ground truth. So we compare the reality that we want to be close to with the actual thing that we predicted. And then we just say, hey, we have basically two things we can do, right? So it can be right or wrong. So it can be, if you look at this table, now when we compare them, it can be red, right? Just ignore what's in there for a moment. So it can be red, which means that's not good. So if it's red, if this color is red, it just means that they do not align. If it's green, then it's perfect, right? They do align, right? And now we can say in which direction they do align or in which direction they misalign. For example, here in the actual classification, we have 1, right? The actual classification is 1. And what we predicted is negative. So we call this a false negative, right? Because we predicted this as a negative, but it's false. So this is how you should remember it. Now, as what do we predict it? As false. We predicted this as false. Is it correct? No, it's negative. It's a false negative, right? So we predicted this as negative, as the negative class. So we have 0 as the negative class in the binary classification, and this is the positive class. So we have to know what the positive and negative class is, right? So negative means this is we predicted this as 0, and it was false, right? It was false. So mean the prediction was false. So the first letter says if it's correct or not, correct or not. And the second is what the prediction actually was. Was it 1 or was it 0, right? 0 is negative and 1 is positive. And now let's go on. The second one, the same thing. And now let's apply this, what we know, to the third one. So we have 1 and the predicted classification is 1. So we look at the second letter. So we know from 1 it's the positive class, right? It's the positive class. So this is P. And is it correct? Do they align? Yes. So it's true. It's true, right? True is good. True is green. It's true positive. Blah, blah, blah. And we have the same here. Now we look at case number 9. So case number 9, we look at the predicted classification first. We can for the second letter we can totally ignore the actual classification. We don't care, right? So the second letter we look, it's predicted 1. So it predicts the positive class, right? 1 means positive class, right? And then we look, is it correct? Does it align? No, it does not align because the truth was 0, so it doesn't align. So it's false. Predicted positive, but it's false, right? Then we move to the next. We look at it. It's 0, so it predicts negative, right? So we'll just look at this prediction. It predicts negative. Then we look, does it align? Yes, it's true, true, negative. And that's it. If you remember it like this, it will be a piece of cake for you, right? So, and then what you can construct, you construct the confusion matrix, and then you just count, right? So just count. You count the number of false negatives, you count the number of true positives, false positives, true negatives, and so on. And you put it in that table. And this table is the essence of evaluating classification. So it's very important that you know this, right? So you have to know where are the true positives, where are the false negatives. So this is always constructed the same. The columns are the predicted conditions, right? So this is what we predict, and the actual condition, so this is our y value, and this is our h of theta, this is our hypothesis output, right? So, and we can have 4 cases, obviously, right? I just showed you. So the first case is this case, where we predicted the positive class. So we predicted 1, and it actually is 1. So this is green, this is great, this is nice, right? The second cool thing is when we predict negative, and it actually is the negative class. So it is 0, right? And this is called true negative. So the diagonal here is always good. The main diagonal is always good. It's green, it's yay, okay? So the other thing is, if we predict negative, you can also do the other way around. If it is positive and we predict negative, so it doesn't matter how you can construct it the way you want it. The important thing is that you get it correctly, right? So if we predicted the negative class, I would always start with the prediction because it's this thing, right? Because this is how we name this is false negative, like I just explained. Like you take care of the second letter here, which is negative. So this means that predicted condition is we predict negative, right? We predict negative, it's n, right? It's n. So, and n says negative, but it's false because the truth is it's positive, right? That's it, right? So predict negative, but it's false. So this is false negative. And here we predict positive, but it's actually negative. So it's false. It's a false positive. It predicted positive, but the prediction is false. This is how you should imagine this, right? And so based on that, we can now calculate it. And we have the total population based on positive and negative. So this is obviously the total that we get, right? P and N. So these are just letters for what we have. Like we're gonna use these short. So this is the predicted positives and this is the predicted negatives, right? So PP and PN, right? And this is positive and negative. Now let me say this is predicted positive and predicted negative, okay? Can I just, let me see. Can I do it a little bit now. Okay. So this is predicted positive, PV and PN. Okay. And now what we're gonna do is we can put these into numbers. So we want this thing right here, right? This is what we want. This is our matrix. And for short, if I put this into short form, I'm gonna leave this out and the matrix will just look like this. So in an exam, it could be I just give you this matrix, right? And then you have to know. Like if I say the matrix in the notation of the lecture and basically the notation everywhere. So I say, hey, this is you have the following confusion matrix. It looks like this. Then you have to know what it is. You have to know that these are the true positives, right? You have to know that these are the true negatives. Now, what was this question? Like this, I know this is a VOD, but what was this, right? We look at it, okay, we have predicted, it's predicted negative, but it's false, right? So this is false negative. Now here, it's predicted positive, but it's false, right? Because it's actually negative. So actually, so this is false positive. It's predicted positive, but it's false, okay? So, and this you have to know, okay? Now, when you have this, you can calculate now based on this, we can calculate the metrics we've been looking for because we want to compress it into one single number. All right. Okay, cool. Now what we're going to do is we're going to start with a number I've been telling you a lot, which is the accuracy, right? And we're going to tell what it does. The accuracy just looks at, and we can have the formulas here. This is blatantly copied from Wikipedia because this is one case where the Wikipedia article it's very good. Okay. So the accuracy, okay, the accuracy just says, okay, it adds the true positives and the true negatives and divides it by everything, like divides it through P and N. So it divides through all the things. So this is basically the question, how many did I get correct? No matter if they are positive or negative class, I don't care about the class. I just want to know how many did I get correct, right? So, and here, if we look at this table, we just have 6 plus 3 divided by 12, right? And this is like 9 divided by 12, which is 0.75, right? So this is the metric we have. So we got 75% correct, okay? This is accurate. This is what accuracy does. Now, the second we have is called the sensitivity, recall hit rate, or true positive rate, right? So usually we use sensitivity or recall are like the things that people use. So you see that they call it different. It depends a little bit on the domain. Like the best thing would be to call it true positive rate because it tells you what it actually is, right? It tells you what it actually is because then you can easier calculate it, right? But sometimes people use sensitivity and recall. Like hit rate is pretty rare, but sensitivity and recall are the more common ones than true positive rate. But true positive rate is nicer because you actually know what it does. Okay, let's have a look. What does true positive rate do? So now we have things that actually focus on the amount of correct predictions. So we will have down here, we will always have the number of ground truth portion of that. So this is now not everything, but this relates either to only the positive or only the negative class. So basically, the true positive rate says how many did I get correct from the positive class? So it's basically like the accuracy, but only for the positive class. So how many did I get correct from the positive class? And why is this important? Because if this is not symmetric, like if we want to predict like cancer, or if the positive class is way more interesting, for example, if we have fraud detection, right? In fraud detection, we care about this a lot. How many did I get correct? How many fraudulent transactions did I use? And we have in the next page, we have an example that will show you why this is very important, right? And why the accuracy is very misleading. So you should never use the accuracy isolated. So this is basically like the accuracy, but only on the positive. So you can see this right here. So the true positives, how many did I get correct of the positive? So out of all the positives, so it looks at this number in comparison to this number, right? And here is the same thing like the true negatives. How many did I get correct out of the negatives, right? So, and we can look at this and it's also 0.75 for both of these, right? So we got 75% correct, 75% correct, okay? And and you can also see here that we can like kind of do the same thing. And so this kind of an average. And now we have something called the precision, right? So this is because people often talk about the precision. I want to show it, but usually these are actually enough to get an idea. And what the precision does, is it takes as a base the predicted condition. So here, this takes all conditions, right? This takes all conditions as base, so the 12, right? These two take the ground truth, or the actual, which is the actual condition. Ground truth is actual condition. Like this is ground truth. This is ground truth. As a base, right? The ground truth P. What's the ground truth? What's the ground truth? And these things here basically kind of look at how they behave, right? So let's have a look. So we also have like the false negative rate and the false positive rate, which is the same here. So this is the opposite of this. Like if you see this here, I wanted to explain this. If I ask you in the exam to calculate the false negative rate, you just calculate the TPR, and this is the opposite. Like how many did I get correct? Like this is a number. How many did I get correct? True positive rate, right? This means that I got the one minus them, I got them wrong, right? So if I get 75% correct, yeah, I get 25% wrong. So this is then 25%. Like F and R needs to be 25. 1 minus 0.725 is 0.75. So it's the 1 minus, it's the opposite. So, and you can remember this, right? If I want to see, this is how many did I get correct? So the question here is, how many did I get correct? Basically not I, but the model. I equals the model, right? How many did I get correct? So, and this is based, how many did I get correct? Okay, and this is based on all conditions. How many did I get correct in compared to the ground truth? So from the positive, from the negative. And now here, let's look at the precision, which is one way. And this is how many did I get wrong, right? So this is basically how many did I get wrong, right? So this is how many did I get correct. And this is how many I get wrong. So let's look. Okay, here changes. So this is also, we take the true positives, right? So we take the true positives. So like we take this, the true positives, and it's divided by the true positives plus the false positives, right? So what we basically do here is, the base here is not the ground truth, but it's the prediction condition, right? It's the prediction. The base here is the prediction. So here's the ground truth, the base, and here the prediction. Because if you look at TP plus FP is PP, right? So it's predicted positives, right? So I could also write PP down here, right? And here we have the negative. It's the same thing. We have the true negatives plus the false negatives, right? Which is PN, right? So remember, right? This is the predicted positive values, and this is the predicted negative values, right? So here the base, here we look out of the ground truth, how many did I get correct? And here I look based on my positive predictions, right? This is the base, here are the positive predictions. So I compare it to this. So how many true positives did I get from my positive predictions, right? And this is a different angle, right? So how many did I get correct? Okay, so let's have another example, okay? I've put, again, the same formulas here. And I want to speak about that example. So in this example, this is what you get, right? So predicted actual, so this is the same form. Usually you will only get this in the exam, right? So this is a case I constructed. And let's say this is your case, okay? And here I would usually ask you what went wrong. And this is a typical case of, now I'm going to pause here 10 seconds so you can think about it. Still watching the VOD. What is this a typical case of? Think of how this actually comes about. What does the model do here? I'm going to give you a little hint. It has something to do with class imbalance. So this is a typical picture you get when you train a model without doing the class, without battling the class imbalance, right? Because what will the model do? The model will say, hey, screw the positive class. If 99% of all cases is negative, I will still get a very high accuracy by just training the model and say everything is negative, right? But remember, in fraud detection, this will look like this, and we're interested in the positive class more than we are in the negative class. But the model obviously says every prediction is negative. You can see we have 0 predictions for positive. There are 0 positive predictions. There are 0 predictions of 1, right? The sum here is 0. We have 0 predictions for positive, right? And all the predictions are negative, right? All the predictions are negative, and we only have like the number of overall cases is this. So all of the cases were classified as negative. And this is something you have to see in the exam and also when you practice this, right? And this is a very extreme case. It could be like there are some numbers here usually, but it will still be biased extremely. Okay. Now let's have a look. And we see that this is biased because here you see the reason, right? You see we have only 42 cases here versus 1,950 cases here, right? So you see that you need to see here immediately that this is a class imbalance issue, right? You can detect it, you can see it. So, and now let's have a look at the numbers. What does this mean? And we see our false friend accuracy. And this is why accuracy is so dangerous to look at SOLE, because look at this. We have such a high accuracy. If I just gave you the accuracy, you would say, let's deploy. But this model would be a danger to deploy, specifically for cases that actually thrive off these of the class imbalance, like prediction of credit card fraud. Do you want a model that says, hey, this is not, that says to every case, this is not fraudulent? It doesn't make any sense. It doesn't fulfill our business goal, right? It doesn't fulfill, if it doesn't align with our business understanding. We are interested in that class. We want to predict credit card fraud. And this tells us, hey, we did a good job. So this is why we need to move to other things. We need to move to things like true positive rate, where we isolate, right? So if I'm more interested in the positive class, I will always calculate things like true positive rate, right? I calculate true positive rate, and of course, true positive rate is 0. So we know our actual positives, right? Our actual positives is 42, right? And out of these 42, how many did I get correct? So it's our true positives, which is 0, divided by 42, which is 0. So, and that means if I counter that, like if I say, hey, can you just give me the false negative rate, right? Can you give me the false negative rate, right? And yes, this is then 100%. So I only have false negatives. It's 1 minus 0, which is 1, right? So I wrote this down here for you. So, and then on the other hand, the true negative rate. So I detected all of the negatives. You can now say, wow, this is great. I detected all of the negatives. Yeah, because everything is negative for the model, everything, right? So, and yeah, the false positive rate is 0. So I didn't accidentally declared something positive because I declared nothing as positive, right? So, and you can see where it comes from. And you can see that this weight drives the accuracy, right? So you can see this here in the formula. This 0 doesn't matter compared to this number, right? So it's only 42. So it's still a high percentage. Like in precision, we cannot do because of 0, but this will be enough for us to see it, right? So This comes, so I want to issue a warning, and I hope you have now understood that it's very important to look at multiple of these metrics. Okay, so now how do we do it with regression? It's pretty simple. In regression, we have a number, right? So this, our hypothesis we'll put out a number, let's say 250, and we will basically have a ground truth, right? Let's say 220, and then we just compare them, and then we sum it up. So we sum it up for the validation data set, for example, validation. Sorry, headphone just went off. I didn't talk. So we just compare them, right? So it's just basically we're gonna have the ground truth compared with the prediction, and then we of course square it so that minus and plus. So if the prediction is large, right? If the prediction is larger, this will be negative. If the prediction is low, this will be positive. And if we don't square it, it will equal each other out. So we have something called the mean square error, which is that. And the problem obviously is that the squared unit cannot be interpreted. Like for example, if we predict the stock market price, like, or the housing price, right? So if we predict housing prices, which was our first example, housing prices in Portland, Oregon, the selling price of a house here is, for example, 2,500 squared, right? And then dollar squared, right? So, and this is a problem because this number is very large and dollar squared is hard to interpret because we want to see what is the mean difference. Like this is the mean difference between the prediction value and the actual one, right? So, and this is why we calculate the RMSE, or often called the Ramsey. some people call it that, the RMSE. And this is what you frequently will see, the RMSE, right? So the importance is this is hard, it cannot be interpreted universally, but it's good to compare different models, right? Because it's an absolute value. You can also have like a percentage error. And what you also should always do, like you could do like max and min. Like this is the same that we discovered when we had it in data understanding, right? So what you can do is like you can have the distribution. You can have the distribution of these prediction errors. This is good advice, right? So so-called residuals, like these are actually the residuals, right? And what you can do, so this is one metric that sums it up. But what you can also do is like you can, like for example, if you have the data table, let me show you. So again, we only need y and theta. So we need the same thing basically as before. And now we compare them. And now what we can do is we can, like, for each of these, we have the residual, which is basically yi minus hx. So we can square this, right? If you want, we can square this. You can also keep it. Like if we want negative and positives, you can actually keep it so that we actually see what is negative and positive. So we can, for example, see if it gets overjudged or underjudged, right? So it could be that the prediction is always a little bit bigger here, right? So let's say the prediction always overestimates the housing price, then this will always be larger, right? So there will be a lot of negatives, right? So it might be better here to not square these things, right? So to not square these things and just say, okay, minus 20, plus 10, minus 20, minus 30. And we see that usually it overacts. And then we can plot this, right? So then we can plot the residuals. We can put them into a plot, right? Where we have like, this is for all our cases, right? So for X, and then we have the residuals here, and we usually have 0 somewhere here. And you know this from regression, but you can also do this with every sort. The residual is just as comparison. We don't need any sort of regression or assumptions. We can just always plot the residuals, right? And so let's just say I have a lot of residuals that are like here, right? So the residuals are maybe not that. So I have a lot that are positive. Then I can say, hey, my model tends to overestimate, right? So if I have a lot of positive residuals, negative residuals in this case, I'm sorry. So it tends to either under or overestimate, right? Because if this is negative, then the prediction overestimates, right? It has a larger number than it actually is. Like it's negative, this is overestimate, and this is underestimate, right? If this is smaller than y, then this is positive. If this is larger than y, so if it overestimates, then this is negative, right? So, and yeah, so this is something I can tell you based on practice you can do to explore the model further, to explore the behavior of the model further, right? Okay, so with that, we conclude our little video on demand. Sorry again, so for putting this on video on demand, but I think it's the easiest lecture to put on video on demand. And of course, there will probably be an exam task related to this because it's very easy. And we also have a task in the preparation exam, and we will go through the task tomorrow. So if you download this on Monday, tomorrow is exam preparation, and we will of course go through the task. We will have another task from the mock exam, and we will go through this, of course. Now with that, I wish you a nice Monday or whenever you're gonna watch this. If you watch this in preparation, good luck. And yeah, we'll see each other tomorrow. Thank you so much, and have a good rest of the day.